Okay. Today, the last thing that we finished off last time is we kind of looked at like a low degree, how to deal with cubics and how to deal with quartics. I'm going to give you a theorem today that shows you actually a big utility of this is it shows how to eliminate certain possibilities for Galois groups if you understand transitive subgroups of SN for the appropriate n. There are other algorithms, right? In fact, if you want to practice this kind of stuff, figure things out, for higher degree things, sometimes you actually have to look at polynomial, you have to think about automorphisms. It can be very specific to the problems, but there are general algorithms. I think the last time I checked Maple, it would compute Galois groups, I think, up to transitive subgroups of SI. So we do up to 90 degree polynomials, and maybe you can do more now. But let me start you off with this theorem, which, like I said, really can be very useful in elimination. So let's suppose theorem. Then I'm going to give you a tail of the Galois group, and then I'm going to tell you a general algorithm that will always you should probably never use it. I suppose that f of x is a monic polynomial degree n. X. And suppose P is a non-zero prime. Let's also suppose the reduction of f of x mod P has distinct roots and some splitting. Suppose reduction of zx, reduction of polynomial f of x by P as n distinct roots in its splitting field. Over. So you take your polynomial, you reduce it by P, you get some other polynomial. Assume this polynomial has n distinct roots over the splitting field of z mod P. So in other words, if you're going to use this technique and your polynomial, for example, is P Eisenstein, you don't want to use the prime P. You can use other primes. Because if it's P Eisenstein, reduction will essentially be x to the n, which doesn't have distinct roots. If f of x factors over zp, let me say reduction. Has, I'm going to call it G1K. And so mi equals the degree of GIX. Then there is an element of the Galois group of F over Q. There's this element of Galois group of F not F bar. So the original F of the Q of the form C1, C2, CK, where each CI and SN is a cycle of MI. So in other words, if this is a fifth, if f of x is a fifth degree polynomial, and in factors is two quadratics in a linear, that means that there has to be an element of the original Galois group that's a product of two cycles, and then a single cycle, which is not there. If this fifth degree polynomial for some other prime factors into an irreducible cubic and a quadratic, that means the Galois group has to contain something of the form ABC times DE. That's what this there means. You can basically look at decomposition mod P, and this tells you it decomposes. There's some element of the Galois group. It has to contain something that has K cycles of length degree of each of these. This is kind of a groovy theorem, and I'll give you an application to teaching as well. So you're going to think I'm freaked out here. This is a proof screen. Example 8, 5, 11. Yes. I'm going to do a calculus problem. So I think I've lost my mind here. But there's a reason for this. I was at Mexico State. I taught a large lecture of polynomial Calc 2 class, and this was one of my problems. This is parabola y, a, x, 1 minus x. So this is the point, 1, 0, right, and 0, 0. And the problem that I asked, and you'll see it's a Calc 2 problem, is find the slope of the line segment such that the line y and x divides region between x-axis and y is 8x 1 minus x forward into two pieces of equal area. Standard calculus problem, right? If m equals 0, well, 1. So as you vary the slope up here, there must be some point where it breaks it into two pieces of equal area, all right? Okay. Well, so how do you go about such a thing? Well, the area under the whole curve is the integral from 0 to 1 of so that's the total area under the parabola from 0 to 1, this thing right here, which turns out to be pull it up, that's going to be 1/2 1/3 x cubed. 1/2 minus 1/3, so I need A over 6. and I want to find the slope such that each of these pieces is 1/12A. By the way, you think I should concentrate on the top or the bottom piece just for fun? I think the top's better, right? Because the bottom involves me doing two ends, right? Do that. So what we want to do here is, let's suppose that this is the intersection point here. I'm going to call this lowercase a in A because the line is easier to do. So what I want to find is I want to find M such that the integral from, see, I guess from 0 to little a of top minus bottom one photo. It may behoove me to find what A is. So notice that A is the intersection of these two, right? So this is also equal to A little a times 1 minus A. So if I set those two equal, MA and of course, I guess you can rather aggressively assume that A is not 0. It's kind of a stupid problem. So and so actually this A turns out to be step. So A is 1 minus M over. Right? So you know what? Since it's that complicated, I'm just going to leave that for now. Let's see what this gives us. Zero to A. I guess this is going to be minus A. Well, let's see. I guess it's going to be A minus M. X. AX minus MX. And then it's going to be minus AX squared. Right. Cool so far? Yeah, you better watch this stuff. So it's A minus M times X squared over 2 minus A over 3 X cubed. 0. Now, of course, when I plug in A equals 0, this is gone. So really the only thing of concern is when I plug in A. But now what? All right, it's a bit of a mess, isn't it? Well, let me fiddle with this. This is A minus M minus 1/3 A times little a all times x squared. Oh, and that should be over 2, shouldn't it? Now, what is, this might actually be useful here. A minus M is, well, you'll see. Notice from this one right here, probably didn't need that part, right? A is A minus M, right? And I'll use that to replace this. So this should be A capital A over 2 minus 1/3 A times A squared is equal to 1/12 A. And this is cool because the A's cancel out, capital A that is. So I get 1/2 A minus 1/3 A times A squared is equal to 1/12. This comes to 1/6. So I get 1/6 A cubed equals 1/12, and I get A cubed is 1/2. And so A is 1/2. And so to answer the question, I guess I did ask for M, right? M I'll go back to this little iteration. M is capital A equals 1 minus A, which in our case is A. There's the answer. And it looked a little bit kind of funny here, but some things canceled out and it worked out right. Really, here's the polynomial part. I had to extract the cube root of 2 here, right? Or cube root of 1/2. So here's where the story begins. I gave this exam in class. Lots of people actually did pretty well on it. 1 or 2 probably got all the way to the end, but like lots of people got 90% of the way there. Well, I had a guy in my class, bit of a slacker, didn't show up. Some other people missed the test too. I was like, okay, you makeup. Well, he didn't show up for makeup. And then, oh, you know, somebody hit me with a brick and, you know, all this kind of thing. So finally, I had kind of given up on him. And he showed up unscheduled. I had like this makeup. He showed up unscheduled. Can I take my test out? I was like, give me 10 minutes. So I sent him out in the hall. And I had this makeup that I had made up. And the only problem that I hadn't fixed with the makeup was this one. It was kind of my centerpiece problem on the other exam. Well, what am I going to give to this guy? I'm not going to give that problem. I mean, that thing's been up on the internet for like 2 weeks now. I got to make it hard, kind of like the centerpiece problem. You can make it. I know. No, we don't look at it. Same problem, same setup. So now I've evolved it around the x-axis. So change the problem. find M such that volumes, or such the volume is cut in half. Right? Same principle. Right now, I'm going to spin this around the x-axis. And of course, this will give me some kind of blob. It looks like, this looks like a really bad, I don't know, it looks like a bad football, I guess. And now I want to find sort of the orange line so that it will cut it into two volumes. And I guess probably my guess is slope would have to be a little bit more, wouldn't it? Right? Because you've got this higher concentration away from the axis of rotation. Right? Same principle. So I wrote this down and I gave the exam. This is a cautionary tale. The key to this problem, the original one, you can couch it in terms of finding M over A, which is what we essentially did. We've got this perfect cube. In this new problem, so in the original problem, basically, is what? One in volume problem. So you had to find the root of a cubic and you could adjust it so the cubic was nice. We got x cubed as one of them. And volume problem, this requires a solution to 8x5 minus 10x4 plus 1. So if you do the analog thing, and by the way, this requires some work. What comes out after this is actually a higher degree polynomial. I got that by doing some reductions first. I think I might have actually gotten a 10th degree polynomial out of this, right? Question is, let us figure out, so here's the abstract algebra application. Is this solvable by lattice? Right? So what we need is we need to find out if this is a solvable subgroup of S5. The subgroups of S5, transitive subgroups of S5, you can take it as read that this is irreducible. There's also one more problem in the statement of my previous theorem, and I did say in the previous theorem that the polynomial had to be mine. But really all you have to do to get around that is avoid not only the primes where this, you have to avoid primes where you have multiple roots in the splitting field, and just avoid the primes that divide the leading coefficient, which in this case is just 2. So we'll skip 2 as well. Transitive subgroups. F5 are S5, A5, 6, 4, 5, the Hebron Pentagon, and Flavinius group 420. If you remember, maybe from 8510, these can all be shown to be solvable. In fact, this was abelian, so it has to be. Yeah, these are all solvable groups. A5 and S5 are not solvable. So it turns out, I'm going to check my factorization. Yes. 11, 8x5 minus 10x4 plus 1 factors this way. 8. So let me point out that, of course, model 11, this is a monic polynomial essentially because 8 is a unit. Model 11. This is 8 times x squared plus 9x plus 6 times x cubed plus 9x squared plus x plus 3. Let's actually check. I want to make sure that we check the details of this. Let's check that the coefficients are right. X cubed, x squared times x cubed is x to the 5th times 8. Got that, right? The chordic term should be 10. Well, let's see, the chordic term is 9 plus 9, which is 18. 18 times 8 is 144. And mod 11, that is 9. 9 is 18 times 8 is 154. Mod 11 is what is it? Yeah. What's it now? That one is negative. So one is. Oh yeah, it's negative 2. Yeah. Thank you. Right, 8. So 8 times 18 is 1, which is negative 10. Thank you. Right. Okay. Let's look at the cubic term. That is 1, and 81 is 82, and 6 is 88, which is 0 mod 11. Yeah, these ones are turned to 0 are nice. Let's look at the quadratic term. That's going to be 3 and 81 and 6, which is 90. Let's try that again. Quadratic term is 3 and 9, which is 12 and 54, which is 66, which is 0 mod 11. The linear term is 27 and 6, which is 33, which is 0 mod 11. And 6 times 3 is 27, which is 5 mod 11. 5 times 8 is 40. Oh, this is 18. 6 times 3 is 18. 6 times 3 is 18, which is 18 times 8 is again 144, which was 1. So this factorization is correct. Now, I claim next that these two are irreducible. Right? So notice we're mod 11. First, I claim that this is irreducible. And the quickest check to do is this. This is the field of characteristic 11, so the quadratic formula applies because you can divide by 2. Right? All we need to do to show that this is irreducible is show that what's under the radical is not a square, mod 11. Look at the discriminant under the radical. You get 9 squared minus 24, which is 57, which is mod 11, 2. Right? Do this. Now, if you look, I'm going to maintain the square of mod 11. X squared. 1, 2, 3, 4, 5. 0, 1, 4, 9, 5. Yes. Why don't I have to make any more? Why don't I have to finish the table? What's the relation from 5 and 6?
6 is -5.
6. This is -5, -4, -3. So they're going to square the same thing. I haven't seen 2 yet. I'm never going to see it. So what's under the discriminant is not a square. Which means neither of these two roots are in Z mod 11, so this polynomial is reduced. The process of checking this one here is just go through and plug in. See, I like cubics, right? Because cubics and quadratics have the following property. They're irreducible over a field if and only if they have no root over that field. No, let me, yeah, that's right. That's right. Because if this were to reduce, no matter how you cut the cake, it has to have a linear factor, which means it would have to have a root. Okay. So if it's got a root, it clearly reduces, and if it doesn't have a root, it can't reduce. Right? If you go through and plug in all values, 0, 1, all the way up to 10, you will find this thing has no root on 11. So therefore, it's also irreducible. Right here, so let's apply our theorem. Since our polynomial factors this way, the Galois group of whatever this was, 8x5 minus 10x4 plus 1 over q contains an element of form cycle. Agree? Everybody okay with that? We'll call this X. What's the order of X? This is obviously an element of S5. It is 6. You all know that one. If you have disjoint cycles, if they're disjoint cycles, then the order is the least common multiple of the orders of cycles, which in this case is 6. It can't be any of those, right? Because 6 does not divide the orders. 6 does not divide 10, 5, and it's divided 20. That means that whatever the Galois group is either A5 or S5. And so, in particular, the student should have shown up for the first exam because he's not going to be able to solve this in closed form. But by the way, which one is it? S5 or A5?
That's fine.
It has to be S5 because this is also odd. That's even, that's odd. So the Galois group was S5. And so we got a lot of mileage out of identifying for one particular prime. This thing had something that looked like a 3 cycle times a 2 cycle. Bang. That means that eliminated everything except for S5. Okay. Any questions on that? Here's another one I throw in here just because it's so freaking fun. And it's quite useful. Theorem. You will see at the beginning that it does specialize a bit, but it's kind of useful. Let's suppose that P is a positive prime. And f of x an irreducible polynomial of degree. If F has exactly two non-real complex roots, and Galois group yes. Has to be full symmetric. Few letters. This warrants some attention, I think. Let me point out that in the kind of degenerate case of P equals 2, this also works. Because if P equals 2, what you're saying is F is a quadratic. And what this says is if it has precisely two non-real complex roots, then Galois group. Because if they're non-real, they're certainly not in Q. By the way, this Galois group is over. I guess it's probably. Anyway, so this also works for P equals 2. Why does it work in general? P divides the order of the Galois group. That was one of our first kind of statements. And Galois group of F is the transitive subgroup of SP. So, what do we know? Well, this means that G, L G so the Galois group has to contain a P cycle. Now notice, this first statement, of course, means that the Galois group has to contain an element of order P. But I've said something slightly stronger. I didn't say it contains an element of order P. I said specifically it has to contain a P cycle. Anybody tell me why? If you're in SP, that's the only way to get something of order P, right? Because in SP, a typical element looks like a product of disjoint cycles, right? Well, those cycles, if it's not the full P cycle, they're going to be smaller than this, and the least common multiple that can never have a factor of P in it, right? So that's kind of special. It contains a P cycle. And since there exists exactly two elements of two exactly two non-real. What does that tell you? There exists an polymorphism. It's pretty filled out. It swaps exactly like these. I've got an affectionate name for this on algebra. It's called complex conjugation. You've got p minus 2 real roots that are fixed, you swap 2. So we have transposition 1, 2 in G. And we have 1 so we'll say that 1 and 2, 1 denotes one of our non-real complex and 2 is the other one. Doubles 1, 2. There's a p cycle, and a p cycle must involve all the roots, right? 1 and 2 may not be next to each other, but they can be. If they're already next to each other in the cycle, I'm done. If they're not next to each other, then I will just, instead of p, I'll use p squared. And if it's 2 steps away, I'll use p cubed and so forth, right? P is a prime, so what is generated by p is generated by any power of p other than the p power. Everybody agree with that? So, G contains 1, 2, and 1, 2, no, here comes after that, a p cycle. And there is a theorem or exercise, probably. I don't know how much you all did this kind of thing, but there's all these kind of generating sets of Sn. In particular, Sn is generated by 1, 2, and 1, 2, 3. So we have, of course, the numbers after 2 don't really matter what order I put them in. We have the 2 generators. It must be a transitive subject of SP. And so, since it has this transitive subgroup of SP, and it's got the generators it takes to make everything. P is important here because it allows me to commute this. For example, P was, instead of being P, if this was like some n cycle, it's not true that every power of an n cycle is still an n cycle. I mean, just look at a 4 cycle, for example. Okay, any questions on I think I probably have just enough time to do this. We can maybe start on finite fields. Probably about finite fields on Friday. We are going to talk about finite fields a little bit, but it's mostly cleaning up stuff that we've already discussed in other contexts. What I'm going to do now is let me describe an algorithm. You can find this, you don't find these things in books as much anymore. It's kind of too bad. I got this algorithm from a book by Eugene Dixon. So suppose that we have algorithm finding Galois. With f of x, let's q of x. And in fact, we could even say cx. Because if you wanted to, you could clear the denominators here. Okay, so how does one go about this? I don't want to reduce one. So first, let's suppose that C1 up to Cn are the roots. Let me point out at this point that these are all distinct because Q is characteristic 0, and we assume that F is an irreducible polynomial. So all the Z's are different. Let x1 up to xn be indeterminates. These are, so you invent a polynomial variable for every one of these roots. So if it's an n-degree polynomial, then you have n new variables. For a permutation, sigma in Sn, we are going to define sigma to be x1 z sigma 1 plus x2 z sigma 2 plus xn z sigma n. So these are permutations. So this is like a big linear polynomial. It's linear in each of the variables. And basically we have an E sigma for every sigma. We go through the Galois group, seeing how they commute the roots. Let G of x this is the product. X is a polynomial variable 2. This is where you should start to realize that this is going to suck really bad. Because if, for example, you start off with a degree 5 polynomial, the degree of this is going to be 120, right? Because you're running through all permutations in Sn. So you get this humongous polynomial. Each coefficient of xi and g, ci is coefficient of xi in g, then CI is symmetric in Z1. So CI, so it turns out to do this computation, CI um, is a polynomial in X1 of Xn. With fractional coefficients. And in fact, in Z, if you made the polynomial Z of the integer coefficients. Now, once this is done, now factor, and this is not an easy thing to do either, factor G into irreducibles. Over X1, X2, C1. These irreducible factors will be unique because it's a unique factorization domain. And let G be the irreducible factor such that E1 is a root. Well, I is identical. That's, of course, one of the permutations, and it's got to be a root of one of these factors. Find that one. The Galois group is precisely all permutations of X1 up to Xn that fits so this always works, but as you can see, it's a mess. It gets out of hand quick. Try this with a quadratic and see what you get, just for fun. You will think it's less fun, but at least you could take comfort in this always works. Okay, any questions?